We import the security library for SHA-256 hashing, plus collection and date classes. The block inner class holds an index, timestamp, transaction data, the previous block's hash, its own hash, and the proof-of-work nonce. All fields are final, blocks are immutable once created. Getters expose block properties. ToString prints a compact summary showing the first 8 characters of the previous and current hashes, plus the nonce. This gives a quick view of the chain's integrity without printing the full 64-character hex strings. The blockchain stores its blocks in a list. The difficulty determines how many leading zeros the block hash must start with, the core of proof-of-work. The constructor initializes the list and immediately calls createGenesisBlock to add the first block. The Genesis block is the first block in the chain. Its index is 0, its data is the string Genesis block, and it uses a string of 64 zeros as the previous hash because there's no preceding block. MineBlock finds a valid hash for this block according to the difficulty. The Genesis block is the first block in the chain. Its index is 0, its data is the string Genesis block, and it uses a string of 64 zeros as the previous hash because there's no preceding block. MineBlock finds a valid hash for this block according to the difficulty. Mining iterates over nonce values starting at 0. For each nonce it calculates the SHA-256 hash of the concatenated block fields. It checks if the hash starts with the required number of zeros, the difficulty. If not, it increments the nonce and tries again. Once found, the block is created. To append a block, we retrieve the last block in the chain, use its hash as the previous hash for the new block, and call MineBlock with the next index. The freshly mined block is then added to the chain. This maintains the linked list structure. CalculateHash concatenates all block data into a single string and hashes it with SHA-256. IsValidHash checks that the hash begins with the required number of zeros, which proves the work was done. The higher the difficulty, the longer mining takes. This method uses message digest to compute the SHA-256 hash of a string. It converts the resulting byte array to a hexadecimal string, ensuring each byte produces 2 hex digits. If SHA-256 isn't available, impossible on standard JDK, it throws a runtime exception. A simple loop calls toString on each block and prints it to the console. This lets us inspect the entire chain and verify the hashes and nonces. The main method creates a blockchain with difficulty 4, requires hash starting with 0000. It adds 3 transaction blocks, then prints the entire chain. Each block's nonce shows the work done. We check the chain's validity, should be true. Then we simulate tampering by replacing block 1 with a forged block containing a different transaction and a fake hash. After tampering, the validation fails because the hash doesn't match, demonstrating the immutability of a blockchain. The output shows the mined blocks with their short hashes and nonces. After tampering, the chain becomes invalid. This demonstrates how blockchain achieves immutability through hashing and proof of work. You've built a complete, working blockchain in Java. This implementation covers block structure, SHA-256 hashing, proof of work mining, chain validation, and tamper detection. Understanding these fundamentals demystifies the core of technologies like Bitcoin and Ethereum.